visible?
Now it is visible.
Yeah. Yes.
Yeah, it's visible now.
Okay.
Your voice is not clear, sir.
Hello.
Yeah,
So
your voice is little bit slower, sir.
now it is okay.
Yeah.
Yeah, it's perfect now.
Okay, okay. So here is the link of the YouTube channel. Uh, you can directly visit that channel also, and the same session is going live at this YouTube also. Okay, along with this Zoom. So here the before starting here there is a message for you regarding staying at home, and very well we are following all the regulations, and we are controlling from the spread of this disease. We have to spread the message to all of your relatives or friends also to follow these rules also. So stay home and stay safe. So interpretation of the IR spectra with the help of some classical examples. We'll go through some examples of IR and how to interpret. As this infrared spectroscopy, it is a basic part of structure elucidation. You can say the preliminary part, and it is not only involved in pharmaceutical chemistry but pharmaceutics. You can say the people from pharmacognosy, they are also using this technique as a preliminary tool for structure elucidation. So once we find out any chemical entity, or maybe it is a natural or synthetic background, so the first part that we are going through the chemical analysis, and after that we'll getting a rough idea about the nature of the compound, and some about the functional groups. But after that we are going through the UV, and after UV we are following the infrared spectroscopy. Okay, so UV is also not giving the much idea about the structure. So you come to know regarding the conjugation is present or not. Okay, some chromophore is present or not. So after that we are following this infrared spectroscopy, which gives idea about functional groups, rough idea about the functional groups. Still the whole structure is cannot be find out. We have to go through the NMR, then carbon 13, and then the mass to further elucidate the structure. So we will go through what we can do with the infrared spectroscopy. Okay. So whatever I am making a marking on the red pen, can you see that marking? This marking I am underlining all. Can you
Yes,
see?
sir. Yes, sir. Yes, sir.
Is it
Yes,
visible?
yes.
Na? Okay, thank you.
Sir, please raise your voice, sir.
Yep. Yeah.
Amar Sheikh, sir.
Huh.
Sir, voice is very low. Please raise your voice.
Okay. 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 Just a minute. Huh?
Oh,
Sir, mute all the participants there.
Yes.
You can mute all the participants. They are speaking like this.
Okay.
Everyone is muted. Only 2, 3 participants are
Yeah. Yeah.
which are not muted.
Okay. Okay. Voice is also 100%. No problem. So I will continue. Now the voice is audible. Is it proper?
Yes, sir.
Okay. Thank you.
Right now it is okay.
Okay, so we'll start with the spectroscopy definition. Very briefly, I will tell very quickly, and then we will be proceed further to our main topic. So, spectroscopy, we know that it is the measurement and interpretation. It is two things: measurement and interpretation of the EMR. Okay. So here the comes. What is an EMR? Okay, so measurement and interpretation of the EMR, which is being absorbed or emitted by atoms, molecules, or other chemical species. Okay, so what is the meaning of the EMR here? So EMR, if you see, it is nothing but the electromagnetic radiation. Okay, like we know the energy is having the various forms. It is transferring in the form of heat. It is transferring in the form of light and the sound. So the energy, when it is transferring in the form of the light with some energy packets, it is known as electromagnetic radiation. And this electromagnetic radiation is composed of energy particles. We say them as photon particles. So these photon particles, they are traveling in the space with the two components. You can see here the two components. One is, you can see this is the electrical component, and perpendicular to the electrical component, it is the magnetic component. Okay. So in this way, the light is traveling in the form of these waves, and this wave is nothing but the electromagnetic wave. Okay. So if I am zooming it, can you see the zoom one, zoom screen zoom? Can you see the zooming of the screen?
No.
Okay. So here, if you see the electromagnetic spectrum, it is divided into the various regions depending upon the wavelength and the energy content. Okay. You are well aware about this concept, energy content and the wave number. So here there are the three waves. I'm giving at A, B, and C. Okay. So here there are the three waves, and if I just draw a, if if I pass them in a same area, okay, let me know which wave will be passing with the more numbers, number 1, number 2, or number 3. Can you type in the chat box which wave will be crossing with the more numbers, number of first wave, second wave, or the third wave? Yeah, thanks for the quick response, Subhash sir. So here, wave number 1 will be passing, maximum wave will be passing in the unit area from the first wave. Okay. Here, if you consider here the distance between these waves, that is known as the wavelength. It is known as the wavelength. So lesser the wavelength, more the waves are passing through the unit area, and more the photon particles will be passing through the unit area. That's why wave number 1 is more energetic, having the higher energy as compared to the number 2 and number 3. That's the relationship between the wave number and the energy. Okay. So you just remember, less the wave number means more the waves are passing through the unit area, means more photon particles are passing, means the wave is more energetic. That's why if you see the laser part, wavelength part of your electromagnetic radiation, that is the gamma rays, very less wavelength but very high energy. You can see wavelength increases, energy decreases, or wavelength decreases, energy increases. So as we go from the left side, we are having the another region, that is again the wavelength is increased, so energy decreased, so we are having the X-rays. And if we move further, then we are having the UV radiations, still the wavelength is more. And if you further go to the again left extreme left, so we are having the visible and then the infrared region. So infrared region comes here. Okay. So why I'm telling you regarding this, because our next session is next slides are related to with this. So here, how the energy is being absorbed. So how the energy is being absorbed by the particles. So here you can consider that is a copper at the ground state, When through these copper ions, if the electromagnetic radiation is passing, what happens? It goes to the higher energy level, that we say at the excited energy level, up, and it absorbs some amount of the energy from these waves. By absorbing some amount of the energy, it goes to the higher energy level. Okay, but how much amount of the energy it is absorbing, that is the difference between the higher energy level and the low energy level. So this is delta E, the ground state and the excited state, E0 to E1. So whatever this difference in the energy is there, same amount of the frequency will be absorbed. That's why it is absorbing the energy and going to the higher energy level. So such type, here we are finding out the how much energy is being absorbed, how much each wavelength is being absorbed. So it is known as the absorption type of the spectroscopy. But what happens in some type of the atoms, some type of the species, they has got the special ability. Okay, once they go to the excited level, they come back to their original ground level, and while doing so, they emits the whatever the amount was absorbed in the form of another radiations, and that is known as the emission spectroscopy. Okay, so if you see the spectroscopy, it is of divided into the two parts, that is the absorption and emission spectroscopy, depending upon the energy is being absorbed or emitted. Okay, so UV spectroscopy, IR and NMR, it is coming under the absorption spectroscopy. So here our IR spectroscopy is nothing but it is the amount of the energy from EMR which is being absorbed. Okay, so it is a you can say absorption type of the spectroscopy. So here it is the absorption of the infrared radiation. Okay, someone please mute the mic. Okay, so here again we see that our infrared spectroscopy is coming in this region, that is -4 to -6. And if you see in wave numbers in this micrometer, it is further divided into the near IR, then middle IR, and the far IR. Okay, so here that is 0.78 to 2.5, that is micron, that is known as the near, then 2.5 to 50, that is known as the middle, and the 50 to 100, that is known as the far. But most useful for the spectroscopy point of view, that is 2.5 to 15 micron. And here it is if you consider into the wave number by some calculations, it is coming into 670 to 4000 per centimeter. Okay, it is in the form of the wave number. So always remember, the most used for our spectroscopy purpose, that is 670 to 4000. Okay, so what is the principle, how the molecule is being absorbing the IR radiations, just we'll see. Here the question comes that whether all the molecules in the nature will be absorbing the IR radiations, or there is some specifications. Okay, so here if you see the molecules which are having the no net dipole moments, they are not absorbing the IR radiations. Okay, so here what is a dipole moment? I will just briefly let you know. It is the separation of the charge with respect to the distance. Okay, if you see somebody, if you please may mute your mic. Yeah. So here, if you see carbon dioxide, it is a linear molecule. Okay, and although there is electronegativity difference between the carbon and oxygen. Okay, but being a linear molecule, the direction of the charge is exactly opposite. Okay, so there is a same magnitude and exactly opposite direction, same magnitude and exactly opposite direction. Because of that, there is a no net dipole moment in this molecule. Okay, now because it is a linear molecule. What if you consider the another non-linear molecule? Here if you consider another non-linear molecule here, so here you can see as this is a non-linear molecule, there is an unequal distribution of the density of the charge throughout the molecule, and here this molecule is possessing some dipole. That's why this molecule is possessing some dipole. Okay, and this will be showing this will be definitely absorbing the IR radiation. So how it absorbs? Suppose for example it is IR radiation. IR radiation, as I initially told you, that it is the pulsating wave. Okay, the electrical component is increasing and decreasing, increasing and decreasing. Okay, and we are having here the this dipole molecule, charge molecule, dipole containing molecules. So here the dipole is a charge distribution. So here, as we are having the wave with the increased and decreased electrical component, so there will be simultaneous there will be si- uh, s- there will be simultaneous repulsion and closeness of the two atoms which are separated by some dipole moment. As the waves is passing, crossing through this, there will be simultaneously repulsion and closeness, and it causes, that is known as the vibrations, that is known as the molecular vibrations. Okay, so the next question comes here, that here I have shown only the one wave. We are passing the IR radiation through this molecule. Okay, means what? We are passing all the waves in between 670 to 4000. All the waves we are passing, these all the waves through this molecule. So here, will all the waves will be causing these vibrations? No, only that wave whose frequency is equal to the this whose frequency is equal to the frequency of these vibrating molecules, vibrating bond, that wave will be causing vibration in this molecule, and that wave, the resonance will take place, and that wave will be absorbed, and the corresponding waves 670 to 4000, all the waves will be emitted, and the detector is detecting that missing waves, and on that basis the peak is observed. Okay, so here what is the vibration in the molecule? All these things you have gone through. It is nothing but the change in the bond length and the bond angle. Okay, so there are the stretching and the bending vibrations. I will not be going in detail, you already know about it, stretching and the bending vibrations. Okay, so here there are the two types of the vibration in all the molecules. One is known as the fundamental vibration, and another is not non-fundamental vibrations. Fundamental vibrations are those vibrations which appear as a band in the spectra. Okay, and non-fundamental vibrations which are due to the result of the fundamental vibrations, will let you know what are those. So we can say the stretching, bending. In case of the stretching, symmetrical, unsymmetrical, bending in plane and out of plane, scissoring, rocking, and these are all the fundamental vibrations, and these are giving the peaks in your IR spectra. But apart from that, we are also having the non-fundamental vibrations, like we have the overtones in case of the aromatic compounds, combination terms, and then in case of the aldehydes, Fermi resonance will these are the other peaks will be appearing, and these are not due to the molecules, but because of the result of the fundamental vibrations. So these are known as non-fundamental vibrations, but mostly whatever the sharp peaks we are observing, that is due to the fundamental vibrations. So we'll see what is the exact meaning of the fundamental vibrations. Okay, so here, how to calculate that a particular molecule will exhibit how many peaks? Okay, how you can find out how we can judge a particular molecule will exhibit how many number of the peaks. So to understand this, we should go through this phenomena that is known as the degree of freedom. Degree of freedom. Okay, so every molecule in nature, every matter in the nature, okay, every molecule, every species, every matter in the nature has got the 3 degree of freedoms. Okay, whether that atom can translate from one place to another place, whether that atom or the molecule can rotate along an axis, maybe x axis or along y axis and along z axis, and maybe that molecule can vibrate. Okay, so these are the 3 degree of freedom which any molecule possess. Okay, so here if if you are considering a molecule, if you are considering a molecule may be consisting of not a single atom, it may be consisting of more than one atoms. Okay, so the total degree of freedom, translational, rotational and vibrational, if a molecule is containing n number of atoms, the total degree of freedom of all the atoms will be 3n. All the atoms will be translating, all the atoms will be rotating, all the atoms will be vibrating. Okay, so the total degree of freedom of the whole molecules containing n number of atoms will become 3n. Always remember this 3n. Okay, so let us consider the case of a linear molecule. Okay, what happens? So here the linear molecule has got translational motions. It can translate along the x-axis, means moving along the x-axis, transferring from one place. It is known as translational motion along x-axis. So 1 degree of freedom, it can translate along a z-axis. So another second degree of freedom, translational motion, and third translational freedom. So 3 type of translational motion is possible in case of the linear molecule. Translational degree of freedom 3. Okay, if I consider the same linear molecule but it's a rotational motion. Okay, rotational motion. So here now it is rotating along say for example it is rotating along y-axis, and it can only rotate along z-axis. Being a linear, it cannot rotate along z-axis. It is not possible for a linear molecule. Only it can rotate along y-axis, or it can rotate along the x-axis. So a linear molecule has got 3 translational and only 2 rotational motion, only 2. So that's why the linear molecule has got 3 translational and 2 rotational freedom. Okay, but if you want to calculate vibrational, okay, so I told you in the beginning that the total degree of freedom including translational, rotational and vibrational is 3n for a molecule containing n number of atoms. So if you want to calculate vibrational, we are just subtracting the translational and rotational 3 plus 2 5 from total. That will be nothing but the vibrational. Okay, so a linear molecule is having vibrational you can say degree of freedom, that is 3n minus 5. 3n is the total and 5 is coming from the 3 rotational and 3 translational and 2 rotational. So it is having 3n minus 5. But if you consider a non-linear molecule now, okay, non-linear molecule, so it can translate along y-axis, it can translate along x-axis, and it can translate along z-axis. So it has got 3 degree of translational motion, 3 degree of translational motion. So you can see the non-linear has got also got 3 degree of translational motion. And now if you consider the rotational motion of a non-linear molecule, so it can rotate along y-axis because it is non-linear. It can rotate along z-axis because it is non-linear, and it can rotate along x-axis as well. So it has got 3 degree of rotational motion. So you can see again the rotational degree of freedom for the non-linear molecule is 3 3, whereas for the linear it is 3 2, because it cannot rotate along z-axis, but it can rotate along z-axis. So
Excuse me, Anwar sir.
yeah,
Anwar sir, can you please adjust your mic, because most of the participants are not getting right correctly.
okay, but if they are going to the YouTube simultaneously, the voice is very clear at YouTube.
But still, if you can, please do this.
Yeah, just a minute. Is it clear now? Can you type, all of you? Is it clear now?
Yes, sir.
Please type in the box. Is it the voice is clear?
Sir, Anwar sir,
Yeah.
just mute all the participants, sir. You have the rights to do that, and they cannot unmute by themselves.
Okay.
By that way, you can undisturbingly give.
Kuchar sir.
Hello. Yeah, I am muted all. Is the voice clear now?
Yes, sir.
Okay. Thank you very much. So I was talking about the rotational motion which is possible for the non-linear molecule. It can rotate along any axis x, y, and z. So it has got the 3 degree of rotational freedom and 3 degree of translational freedom. So if you want to calculate the vibrational frequency, vibrational freedom for a non-linear molecule, we have to calculate translational and rotational from the total. Okay, so that is 3 and minus 6, because 3n is coming from the total of rotational, translational, and vibrational. So in reverse way, if you want to calculate the vibrational, we have to subtract the translational and rotational from the total. So 3 and minus 6. Okay, so this many number of the vibrations will be possible for a non-linear molecule. 3n minus 6 and 3n minus 5 for the linear molecule. So let us see here I am showing you a non-linear molecule, translational and rotational both. Now the molecule is rotating along y-axis and it is translating along y-axis. So it is having 3 plus 3 translational. In the same way, it is rotating along z-axis and it is translating along z-axis. Okay, and in the same way, it is rotating along x-axis and it is translating along. That's why total 3 plus 3, 6 rotational and translational. So its vibrational will be total 3n minus 6. So just see here. Let us calculate for the water molecule. If you take the IR of a water molecule, how many peaks are expected for the water molecule? So as the water molecule is coming under the category of the linear molecule, okay, so we have to use the how many vibrations will be possible for the water molecule. So we'll be using the formula uh, that is 3n minus 6. Okay, and if you calculate, it is 3n minus 6, it is coming to be the 3. So if you see the this IR spectra of the water molecule, we will be getting these 3 peaks. Okay, it is a non-linear molecule, so we are using 3n minus 6. Okay, where n is the number of atoms. So 2 hydrogen, 1 oxygen. So 3 into 3, 9 minus 6, it will be coming 3. So we will be getting 3 peaks for the water molecules. So what are those 3 peaks? The symmetrical, an asymmetrical stretch, and the scissoring or the bending. So these are the 3 peaks are possible for the water molecules. So any atom, any molecule, if you know the structure and if you know the total number of the atoms in that molecule, if it is a non-linear molecule, putting into 3n minus 6, you can just expect how many peaks we can expect in the IR spectra by using this formula. So here I will not go through it, but how the frequency is being calculated by using this Hooke's law, because it is not the part of that, but there is a formula by which for example, you can say the carbonyl stretching is the ketone is of that is 1710 for, yeah, it is for carboxylic acid 1715, for amides it is less than 1700, 1600 something. So where from this all calculated, it is the calculation using this Hooke's law. So we'll not go through it, we'll directly go to the interpretation of the IR spectra. Okay, so here why if you're getting any spectra of any unknown compound, okay, if you're getting the spectra of any unknown compound, so I have made a simple rule of dividing that spectra into 5 zone. There's a 5 zone formula you can apply, and you can very well interpret any of the compounds maximum functional groups. So 5 zone formula. So say for example, this is our one of the unknown compound having this IR spectra. So here What you have to do, you have to divide the IR spectra into 3 zones. I'm explaining zone 1. Just with a pencil you have to draw the line on your IR spectra, and zone 1 is comprising of 3200 to 3700 per centimeter region. Okay, now here zone 2, that is 2700 to 3200. Okay, I make another lining at 2000 to 2300, make another band at 1680 to 1850, and make another band at 1450 to 1680. Okay, this is known as the 5 zone analysis or solving any complicated IR spectra. Now why I made this 5 zone? Okay, there is some background behind this. So here what is the meaning of this 5 zone? Any all the characteristic peaks of the functional groups are, you will be finding in somewhere in these regions, either from 1 2 3 or 4 or 5. What about this region which is at the extreme right of 1500? What about this region? Okay, so here this region is known as the fingerprint region, and here very specific peaks are appearing. Very specific peaks of the molecules are appearing. Very fixed peaks are appearing here. So this region is not giving much idea about the functional groups, but here we are getting the much idea about from the left hand side of the right hand side of the 1500. So we are dividing it into the 5 zones. So please note down these zones. Okay, so I will again repeat, what is the zone 1 comprising of? So here what is the zone 1 comprising of? Zone 1 is comprising of all the various bands that will be appearing of alcohol, and you can say you can say alkynes, CH, and the amines. So if you are getting any peak in this region, that is zone number 1, it is indicating that the compound may possess the alcoholic OH group or the alkyne SPCH, SPCH, or the amine, or the amide NH. If you are getting some peaks in the second region, that is zone 2, I told you that is 2700 3200. It may be because of the sp2ch, mostly the ch is stretching, which is connected to the sp3 carbon, sp2 carbon. Okay, or you will be getting the aldehydic ch or the carboxylic oh. So just remember here, if you are getting any peak in that region, maybe something from this 4 will be there. Now zone 3, if you are getting some peaks in this zone 3 region, it indicates that some triple bond is present. Okay, that is 2000 to 2300. Maybe the C triple bond C or C triple bond N, nitrile, or these acetylene alkynes are present. Zone 4, it is known as, we have given name, it is a C double bond region, carbonyl compound region. So mostly it is comprising from 1650 to 1815. Okay, so maybe the ketones, esters, aldehydes, carboxylic acids, or amines, they are having a sharp peak in this region. That is zone 4. Remember zone 4 for the carbonyl region. And the last one, that is next extreme left, right to the 1500, that is 1450 to 1680. It is a double bond region. So maybe the C double bond C of aliphatic compounds or C double bond C of aromatic compounds. Here we will be getting the peak in this region. So here this 5 region is very important. I am again revising zone 1 alcoholic, or that is this alkyne CH or the amide NH. Zone 2, that is the sp3 CH or the aldehydic CH or the carboxylic OH. Zone 3, that is 3 bond region, triple bond region, maybe C triple bond C, C triple bond N. And zone 4, that is carbonyl region, and that is zone 5th, C double bond C aldehyde, that is you can say aliphatic or aromatic region. Okay, so this will help a lot while finding out the some unknown functional group of your given spectra. So let us start here. First of all, the very important point regarding the carbohydrates. hydrocarbons. Here CH stretching, CH bond, carbon and hydrogens are present in all the organic compounds. Okay, so your drugs, your maybe it is a natural molecules, they may be containing the carbon and the hydrogen. Okay, so how this carbon and hydrogen is connected together, it gives a lot of information about the structure of the molecule. So this CH bond, okay, maybe this hydrogen is connected to yeah, say for example the triple bond carbon. Maybe the hydrogen is connected to double bond carbon, or maybe the hydrogen is connected to a single bond carbon. You consider, you can take out any molecule in nature, starting from the benzene to the cyclohexane to the more complicated you can say the natural compounds. You might be finding at least a CH in that molecule, at least a CH bond. Okay, so and that CH may be connected to a single bonded carbon, or that may be connected to double bonded or triple bonded. So that gives a very nice idea about the structure. If your CH bond is connected to a triply bonded carbon, means it indicate that it is a you can say sp hybridized carbon, sp hybridized carbon. And you know that sp hybridized carbon, here the sp, so here 50% s character is there. Okay, as the 50% s character is there, the overlapping is also the center of the overlapping, the bond cloud is shifted at the center, and this bond becomes little bit stronger one if it is connected to the sp hybridized carbon. So more the stronger bond, more the force constant, and higher will be the frequency. That's why the hydrogen which is connected to the sp carbon, it is giving a peak in the region of 3300. Always remember this. If it is hydrogen is connected to the triple bonded carbon, it is giving in the range of 3300 per centimeter. Now in this case, the same hydrogen, it is connected to a double bonded carbon, means it is a sp2 hybridized carbon. sp2 hybridized carbon means what? It is having 33 percentage of the s character, because sp2. So if you consider sp2, it is 100%, where uh, s is only one and p is twice, so it is coming s character is coming to the only 33 percentage. So this bond is comparatively weaker as compared to this bond. So weaker the bond, here less will be the frequency. So it will be having the frequency of vibration 3100. Okay, so it is having 3100 per centimeter. Now if you come to the sp3 hybridized carbon, single bonded carbon, sp3 hybridized, all single bonds. So here you can consider the s character is s and p3. So total 4, 1s and 3p, total 4. So s is 25 percentage, so, and p is 3, so it's 75 percent. So it is s character is only 25 percentage. So this bond is again little bit more weaker. So more weaker, lesser will be the frequency. That's why the ch is giving here 2900 when it is single. So somewhere we'll be finding this like methyl group, then ch2 group. Okay, so here this information will be needed there. Just remember it. Alkyne ch 3300, then alkene ch 3100, and alkane ch 2900. It is very very important, because somewhere in all the drug molecule these groups are present. So let us take one example. So here take the molecule that is decan. Okay, decan ch3 ch2 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 and then ch3. Okay, this is a decan molecule. So simple alkane, you can say straight chain alkane. Okay, so if you see here how to solve the spectra, whenever you are getting the spectra, you do one thing. You just draw a line here at 3000. You draw a line here at 3000 and draw another line at 1500. Okay, draw another line at 1500. So here we'll be finding here just at the extreme left of your 3000 near about 2900. You can see here near about 2900 you will be finding this peak. Can you see this peak? Okay, so it is due to, as we have discussed earlier, it is due to the CH stretching in this molecule. Maybe you can consider this yeah, it is a CH3 group, this or this is the CH2. So it is due to this CH stretching. So here we'll be finding here. Then another, we are not getting any peak in this region on the extreme right side of the 1500. So here we are explaining on the basis of this. Okay, because there is no other functional group is present here, only the CH stretching is there, only CH stretching and bending vibrations are there. Okay, now if you consider the another molecule, say for example the below one, here that is one heptine is there, so it is containing here the triple bond, and you compare both these structures. So I am again drawing a straight line from 3000. Just draw a line from the 3000 and draw a line at 1500. Now here there is a some difference in the spectra you will be observing here. First of all, just see the extreme left, extreme left here of these 3000 extreme left. You will be finding here the peak less than 3000. That is 2900. It may be due to CH stretching. Maybe you can say here the CH3 group is there, CH2 group is there. So it is due to the CH2 stretching. Now, if you see here, that is 3000. 1, 2, and 3, 3300, near about 3300, this region. You are getting another peak at 3300. So this may be, you can see here, this hydrogen which is connected to the triple bond. Okay, so you can see here there is a CH. So this CH triple bond, and this is for the single bond sp3. This is, so it is giving at 3100. This is another peak. Now, if you draw a line at 1500 in the left hand side of this, if you go to this extremely at 2001, 2100, near about 2100, you will be getting this peak. And if you written down that 5 zone, I have told you that is zone 3, that is C triple bond C or C triple bond N. So this peak, it is appearing due to the carbon-carbons triple bond. You can see here CC triple bond. Okay, so these are the characteristics peaks which are found here. So here there is a difference here you can be finding, because there is no triple bond in this molecule, and here is the present, so we are getting the extra peak. And there is another difference here, so there is no hydrogen connected to the triple bond in this molecule, but it is there in this molecule. Okay, but there is a similarity here, but because of that CH2 CH2 stretching, which is common in both the molecules. So here, with the help of this IR, we can differentiate these two molecules. If you go proceed further, there is a alkene. Okay, there is another example of the alkene. So in this alkene, again, if I draw a the very first part you have to do is that draw two lines in the spectra, one line crossing the 3000 and one line crossing the 1500 in your IR spectra. Immediately draw these two lines. So extremely that is near to the, that is 3000, that is 2900. If you see this peak 2900, again I told you it is due to the CH stretching, sp3 CH stretching. Okay, and if you see the other two peaks that we'll be observing here, it is just at the just next to 3000, that is 3100, not 33, 3100. And if you see our previous example here, the hydrogen which is connected to three double bonded carbon, it is giving the peak in the range of 3100. So here it is due to, say for example, if it is a carbon and any hydrogen is connected to it, so this peak is due to this CH stretching, and this peak is due to CH stretching of single bonded, maybe this CH3 or CH2, CH2, CH2. Okay, so these two peaks are clear. Okay, and if you draw a line at 1500 and go to the extreme left, say for example it is 1600 and 1700, the peak is appearing between 1600 and 1700 somewhere here. A peak is appearing between 1500 and 1600 somewhere here. And if you see our fourth region, what I told to you here, this one, okay, so it is a double bond region. Okay, so it is due to C double bond C, this one. So we'll be majorly of looking into the three peaks here: the peak due to 3100, the peak due to 2900, and the peak at that is you can say 1650, which is clearly indicating that the your molecule is say for example it is a alkene. There are some peaks here, you can be observing some peaks here. These peaks are very very fingerprint peaks, and these will be specific for the compounds only, but major the left hand side right hand side of your 1500, that will be giving idea about your functional groups. Now if you see the aromatic compounds, say for example this is toluene. Okay, you can compare the toluene with this aliphatic alkene and then aromatic now. So toluene, so again you draw a line here at 3000, straight line, and another line at 1500. Okay, so what are my findings now? Here will I am finding again this shoulder peaks and one peak here, and I will expect it is due to 2900 sp3, that is CH, maybe a CH3 group connected here. Okay, so this CH stretching 2900. But if you see the 3100, you will be finding here one more peak 3100. So which peak I told at 3100? Can you type in the box which peak I told at 3100? Can you type in the box, chat box? Can anyone answer? Yes, very good. It is thanks for the quick answer. Yeah, sp2sch, great, great, great. No, it is sp2ch. Yeah, so you will be finding here this is the ch2, this ch2, and these two hydrogens are connected to this double bonded carbon. So we are getting here 3100, this 3100, that means due to this ch, and we are getting here 2900, 2900. You can consider SCS3 here, because this CH3 is sp3 CH3, so 2900, and this CH is connected to the sp2 carbon, so 3100. These two peaks are clear to you. Now, if I draw a line at 1500, I always told you to draw two lines, okay, at 1500 and 3000. So extreme this you can see here a peak that is due to near about 1600 or 1580. It is due to C double bond C of aromatic. Okay, C double bond C of aromatic. So you may be thinking one thing here, that the C double bond C, the same thing I told in the earlier case here. I told this C double bond C, but it is appearing somewhere at 1650, and here you can say it is appearing below 1600 or near about 1600. Okay, both are the C double bond C, but the value is a little bit different. It is 1650 and it is less than 1600. So it is because aromatic C double bond C appear lesser than that of the aliphatic C double bond C. Okay, can anybody tell the reason why aromatic C double bond C is appearing at the lesser value that as compared to the aliphatic C double bond C? What is the factor? Yes, I will appreciate the quick answers. Very correct. Very right, very right. Because of the resonance and conjugation. Very correct. So here I will appreciate your answers. So here, and why it is so? Because of the resonance, this double bond is rotating. You will be you know this, and you are writing the actual hybrid of the benzene as with the dotted lines. So sometimes it is a double bond and sometimes it is a single bond. All the time this character is not a single bond. Okay, and that is the reason, as you know, that a double bond is occurring at slightly the lesser frequency as compared to the single bond is giving frequency as lesser as compared to the double bond. So as in case in this aromatic case, the double bond is not all the time the same double bond, because the resonance sometimes it is a single bond and double bond it is revolving, it is resonating. That's why it is appearing little bit at the lesser value. So here these are the second thing we will be observing. But here you will observe a very characteristic that you can note down in case of the aromatic compounds. It is known as the combination of the overtone bonds. This combination you will be observing near about you can say here 1600 to 1700. Here you will be observing these small peaks. It is very specific for, and you can say the aromatic nucleus is present. It is because of the aromatic nucleus, which is this pattern you will not find in the above case because it is aliphatic one. Okay, so that is the difference between these two. And here this another peak, it is a due to the CC bending. That is also the characteristic in the fingerprint region due to the this in case of the aromatic compounds. Okay, so you can see here, you can find out the difference between the aliphatic and aromatic compounds. Now here is the example of uh, another case. I will ask one question here. See, here is the you can say butene. You CH3 is there. You can consider CH3. It is a butene. Okay, you can consider CH3 here and H here. Okay, this CH3 H. So in this case again, if you draw a line at 3000 and 15,000, okay, so there is no dot. You will be getting this CH stretching of the sp3 carbon. These two, or this CH stretching. There is no dot. We are getting here. Okay. Uh, and one peak we are getting here. at 3100, 3100. It is CH stretching. But here, as it is an alkene, my question is that ideally due to this CC stretching, we should have get a bond in the region of say for example 1650 here, as we got in this case double bond CC stretching due to this CC stretching. But here we are not getting this bond, even C double bond C is present there. So what may be the reason? Can you explain why it is so? Ideally, by the law of your IR, there should be a peak of C double bond C, okay, because it is an alkene. So in 1600, no steric hindrance will not be there. Yes, can anybody explain it? So what is that? Why there is not the peak? Even it is a alkene, but there should be the expected peak. Okay, but it is not there. So here initially I told you one thing regarding the dipole moment. Okay, so as it is a cis butene, as it is a cis butene. So if you see here, if you divide here, the dipole moment, okay, here the dipole moment, the charge and their direction, it is exactly opposite to each other. You can see here. And what happens here? The net dipole moment in this double bond region is nullified. The net dipole, because it is a cis butene. So in this region, the dipole moment is nullified. There is no dipole moment, and because of that, it is not showing the absorbance of the this C double bond. But if you consider, if you take the IR spectra of this trans butene, definitely there will be the peak. So that is a difference between that is the importance of the dipole moment also you can consider. Now in case of the alcohols here will be again, you if you draw a line at 3000 and 1500, yeah, dipole moment is cancelling. If you draw a line at 1500, so here again there is no doubt we are be having here a lot of CH stretching. So at 2900 we will be getting at sp3ch, sp3ch here. But at the extreme right, you can say here we are getting a broad peak. We are getting a broad peak. Okay, say for example in this you can say 34 to 32. It is a broad peak you will be getting. So this broad peak is due to this OH stretching. But the question is coming that why the peak is broad? Can you tell me that why the peak is broad? Why not it is sharp like that amines? Amines are also giving in the same region. So yes, very good. It is due to the hydrogen bonding. So if you consider the alcohol molecules, if you consider the dimer of the alcohol molecules, so these alcohols are connected to each other like this. Another molecule of the alcohol. So due to this hydrogen bonding, the peak is appearing as a wider peak, and this is the very specific. Like the shape of this peak is like if you're keeping out your tongue outside your mouth, so that peak is appearing like the tongue. If someone is keeping out the tongue from the mouth, so it is a specific peak for the alcohols. uh, but if you see the case of the below, these are again the alcohols in the below. If you see, this is also an alcohol example of the same one. So here if you see carefully the spectra of these below molecules, I am just drawing the two molecules together. So in this case, the OH peak is appearing as a sharper one, not as a broader one. So here, what may be the reason? Why in this case, the lower case, the peak is appearing as a broader one? Yeah, can anybody? Here in this case, as these are the bulky groups which are present here, the bulky groups, and because of the bulky groups, the steric hindrance is too much, so that here there is lesser possibility of hydrogen bonding in this case. Okay, there is a lesser possibility of hydrogen bonding in this case, and because of that, in this case, the peak is appearing as a sharper one as compared to the earlier cases, the one it is coming under the same OH group. If you see the another molecule like carboxylic acids, okay, so in case of the carboxylic acids, here again there is a possibility of the hydrogen bonding. If you see the dimer of the carboxylic acid, okay, so there is a possibility of the hydrogen bonding, and these hydrogen bonds are very stronger one, okay, as compared to the alcohol. So here again we are getting a broader peak of the OH in this region, okay, and along with that you will be getting the very specific peak of the this C double bond O is I told you in the fourth region, okay, C double bond O region. So if you draw a line at the say for example 3000, you will getting a shoulder peaks, maybe due to this CH3 stretching, this OH due to carboxylic OH, and here another line if you draw at 500 just extreme right, you will be getting a sharp peak. This is identification of the, you can say, the carbonyl group. So it is appearing somewhere around 1600, 1610 or 15. This is 1600s. Sorry, 1710 something. So this is the specific peak, very characteristics and very sharp peak. Okay. If you see the difference of the dipole moment here between the carbon and the oxygen, see this difference of the carbon and oxygen, there is a greater electronegativity difference. So the dipole moment which is created between the carbon and oxygen, it is having of the greater magnitude. And as it is having the greater magnitude, the you can say the K value or the force constant is a little bit more. And because of that, the peak intensity is very sharp. Okay, that's why this peak is a very characteristic and very sharp peak is appearing in this 1700 region. Okay. Now, if you go to the this structure, is an amine. Okay. So again, as per our rule, we will be drawing a line at say for example 3000 and another line at 1500. Okay. So here you will be our as usual you will be getting here the solder peaks 2900 due to this CH stretching of sp3 carbon. Okay. And here along with that, if you see this side, maybe in that 3400 to 3300, if you are getting this peak, okay, so this peak is due to this NH stretching. Okay? This peak is due to NH stretching because here OH and NH is giving this peak. I told you in the beginning that region number 1, if you see here, you can see amines and OH, okay, and alkynes. So here you will be getting this peak due to the NH. Okay. Now this NH, if you see whatever the peak you are getting here, NH, this peak, Okay, a smaller peak is appearing here. And if you see the below structure, if you see here the below structure, it is also an amine. It is also an amine. So here you just draw a line here at 3000 and draw a line at 1500. So if you see here, you will be getting a two peaks here. Okay, so maybe the two you will be finding here it is a stretching vibration. So here the two hydrogens are connected with the nitrogen. So you can consider here both are going simultaneously away from each other, that type of the symmetrical stretching. So you'll be getting one peak due to that one, and one is coming toward the nitrogen and another is going away from the nitrogen, asymmetrical stretching. So the another peak is appearing due to that one. So the peak is bifurcated into two because it is a primary amine. Okay, so that is the difference between the secondary amine and the primary amine, you have to remember. And if it is an aromatic amine, for example aniline, so what will be the difference you will be finding here? You will be getting here these two, because NH2 group is there in aniline. Okay, so you will be getting the this two. Along with that you will be getting the aromatic characters, overtone peaks here, and along with that you will be getting that is near about 1600 or 1590, a peak of the aromatic C double bond C, and one characteristic peak here. So that is, you can differentiate between the aromatic and aromatic amine and secondary amine and the primary amines. So this is the major difference between the secondary amine and the primary amine, you can see. So this is the spectra of the amines you can consider. Now if you consider the spectra of say for example these anhydrides, in case of the anhydrides you will be getting here the peak due to this carboxylic. Okay, maybe in this region, the peak due to this carboxylic acid, it is bifurcated into two. Okay, and again the reason is that the same thing, it is due to the symmetrical stretch, one peak, and due to the unsymmetrical stretching, the another peak. So here the peak is bifurcated into the two at that region due to this you can say the symmetrical and asymmetrical stretching. So here we can consider the example of the unsymmetrical symmetrical stretching. Now if you go to the major class of the compounds which are having this carbonyl functional group. Okay, so it is very interesting to know about this carbonyl functional group. If you consider the carbonyl carbon, it is present in amide also, carboxylic acid also, ketones, aldehydes. You can consider the esters, anhydrides, and acid chlorides. Okay, so here the band is starting from carbonyl compounds, maybe present in any group from 1650 to 1850. You will be observing the very strong band in this region. Okay, but depends on which carbonyl carbon it is, so the values changes. So if you just at the middle you divide the this at the middle and somewhere around 1740, this line, I'm dividing this line. So I'm getting the extreme right side of this line and extreme left side of this line. So there is a interesting point to remember, to note here. If you go 1740 to the right hand side, we are having here you say for example this C double bond O, which is of an ester. Okay, C double bond of an ester. So here this ester C double bond O, it is connected to a you can say this alkyl group, which is say for example electron donating. And here there is also, you can consider the uh, inductive effect here. The inductive effect is operating here. So here the inductive effect is increasing the electron density here. Okay, and due to this inductive effect here, the electron density is increased, so this double bond character remains maximum as a double bond. Okay, so I told you if double bond goes to the single bond, means say for example this situation, the values decreases, and if it remains as it is, the values increases. Okay, so because of that, these esters, inductive effect is more operating than that of the resonance here, okay, in this region, and the double bond character is increased. So here we are getting here somewhere in the region of more than 1750, 40, 1745 ester C double bond O. But if we proceed further here, ester to the anhydride, so here we are getting here more stronger inductive effect, okay, and due to this more stronger inductive effect then the resonance effect, here we are getting this the stronger frequency 17 19 near about, we are getting a peak of anhydrides. And if you consider to this third case, more stronger say that inductive effect, more stronger inductive effect. So here we are getting the still higher values, that is coming to be, say for example 1800 or it is 1815. So values are increasing due to the inductive effect. Inductive effect is prevailing here. But if you go to the left hand side of this 1750, we are having here the, say for example ketone. Due to this ketone, what is happening here, the inductive effect is causing, and this double bond density is just double bond density is going on to the oxygen, making it a single bond. So here we are getting the decrease in the frequency near about 1725. But you compare the ketone with the aldehyde, this aldehyde with the ketone. So here we are having the two alkyl groups. So it is a strong inductive effect prevailing here, and that is further decreasing the values, to 1715. And if you still proceed further to, say for example the carboxylic acid, okay, so again here the values is further decreasing to 1710. And if you go to here amines, so due to this resonance, here resonance is prevailing, so this is completely a single bond is converting, so very less amides near about 1650. So that is the difference between all the you can say the this carboxylic acids or ketones, okay. So while analyzing, we have seen some spectra like regarding our aldehydes, ketones, alcohols, aromatic, aliphatic. So if you are analyzing the IR spectra, first of all see whether your compound is containing a bond at for the carbonyl group. If it is there in this region 1660 to 1820, means this region or this region, okay. If it is a band is there, you can again check whether another band is appearing at this OH group. So it may be indicating that a carboxylic acid is present. If along with this C double bond O some NH stretching is present, it is indicating that amide is present. If along with the C double bond O, if another peak is present in the region of 100 to 1300, you will be getting consider it as an ester. Along with the C double bond O, if you are getting a CH stretching, it may be an aldehyde, okay. And here along with the C double bond O, if you are getting no OH, NH, CO or CH, so it indicates that a ketone is present, because on both the sides CH3 is present. If along if there is no C double bond O in your spectra, you check for only the OH is there, okay. A broad OH peak is there, it is will be indicating that a alcohol is present. If there is no C double bond O peak, check for the sharp peak. Broad is for alcohol. If this in the same region, if the sharp peak is present, so you can consider is amine. And if the sharp peak is divided into two, you can consider as a primary amine. If there is a no COH group, no OH group, check for the CO in the range of 1300, and it will be indicating an ether. And look for the C double bond OC, that is indicating the aromatic and the overtone peaks. So these are the some hints you can apply if you get some unknown spectra. Now here, is it audible now?
Yes, sir.
Okay. Is it audible now?
Yes, sir. Continue.
Yeah. So here, let us have some examples here. Now we are having a spectra here, and say for example, I'm giving 1, 2, and 3. Three compounds are there. Can you tell me the probably this spectra is related to which compound? 1, 2, or 3? Quickly tell me. Somebody is saying 3. Somebody is saying 2. Okay. 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 Okay, we'll check. Very correct. Very nice. Very nice. Very quick response. Fantastic. Very fantastic. Very active members. So here we will rule out one by one. Okay. So in this case, if you see the first thing that will draw a line at 3000 and a line at 1500 as per our rule. So we'll be getting here. What are these peaks? It is sp3ch. That is also present here. It is also present here. It is also present here. So this peak will not be the indicating to identify from all of the three which we have to identify. Okay, this one. It is present in all three CH stretching. Okay. Now 3000. Extreme left to this 3000, we are observing a peak here. Okay. Now here I told one very specific thing regarding the alcohols. OH, that alcohol, like I told you to remember that just remove your tongue outside your mouth, and how it looks, the similar peak will be appearing due to alcohols because of the hydrogen bonding. Okay. So here comes that whether it is OH of carboxylic acid or OH of this alcohol, because it is not NH2. If it is an NH2, this peak might have divided into the two, because as I told you earlier, because it is a primary amine, always divides into the two. So we are ruling out this molecule. This is not our answer. The answer may be from these two. Okay, so let us see. So the difference is that OH is present in both carboxylic acid also and alcohol also. But along with in this molecule, we are getting a carbonyl functional group. And I told you carbonyl functional group is having a very intense peak, very sharp peak, very sharp peak. I will go back to this carboxylic acid, C double bond O, it indicate. Okay, C double bond O, no? And in this case again, I told you in this, yeah, carboxylic acids. So 1710. Okay. So if you see here, there is no sharp peak in this region. 1700, you see 1600, 1700, and somewhere here, there is nothing. So we can ruling out this structure. So we are finally we can say it is an alcohol. If you see the another example here, again there are the three structures in front of us, and just can you tell me the structure is belonging to which one? I'm giving the number. So can you tell me the spectra is belonging to which one? Okay, so we'll see one by one. Okay, so if we see here again, as per our rule, we will draw a line. Sorry, because line is not straight. You consider that is straight line. Okay, if we draw a line at 3000, and draw a line at 1500. Okay, so no doubt we will be getting here CH stretchings. Okay, that may be present here also, it is present here also, so it is not giving much idea about identification in all the three structures. Okay, CH stretching. But if you see here, we will observing this peak that is at 3100. Okay, next to this, I mean, the 3000, this is 310, and a peak is appearing here, 3100, this peak. Okay, 3100 peak. So just remind what was the peak I told you in the beginning at 3100. If you see, if you recall, yes, very good. It is SP2. Okay, so it is SP2. At the beginning, I will just let you know it will be 3100. Okay, and it is SP2. I will come back. So this peak may be due to the sp2 double bonded sp2. Okay, so you can see the double bonded sp2 is also present here, and double bonded sp2 is also present here. Okay, as there is no peak in the triple bond region, you can see triple bond region that is 2000 to 2001 2003, there is no peak, so we can ruling out this molecule because in the triple bond region there is no peak. So less possibility of this molecule. Now we have to divide, we have to consider whether the molecule is from this category or this category. Okay, we cannot consider from, because both only sp2 we find it out sp2 which is also present in both. Okay, now if you see carefully here, that is 1500, 1600 and 1700. In between 1600 and 1700 we are getting this peak. Sorry, okay, in between this is 1500, so 16 and 1700, and this peak is appearing in between these two. Okay, 1600 and 1700. So I told you one thing regarding this, that 1600 and 1700 the peak is appearing due to C double bond C. The peak is appearing due to C double bond C. Okay, so answer may be from here or here, but if you consider here, we have to find out a peak due to C double bond O. We have to prove a bond due to C double bond O. Okay, and if it is, you consider a ketone, so just see, in a ketone the peak should be at 1750. Okay, if it is a ketone, so we should have get, this is 1600 1700, we should have get a very sharp peak in this region if you want to prove this molecule. It is not like that, so we are rolling out this molecule because it is C double bond C stretching here. Okay, so in that way, the another example is also there. Instead of I am writing here A, B and C, because 1 2 3 already we have written in the earlier example. So just guess what is the answer. Okay, very nice, very quick answer. Some if your others are also replying, I given A B C, not 1 2 3, please. Yeah, yeah. So here we'll see the case. What is the example? That shows that if you draw a line at say for example 3000. Sorry. So if you draw a line at 3000, and if you draw a line at 1500, always we are there doing this practice. Okay, so 3000 extreme right, we are getting a very small peaks that may be due to CH stretching, which is also present in every compound, so it is not total indicative. The other peak we can see here. So here I am finding here, say for example it is 1500, 1600, 1700, 1800. So near to that 1720 or 1715, I'm getting a very sharp peak. I told you this very sharp peak in this region, that is due to C double bond O. So we are ruling out this molecule. So our answer is from these two. Okay. Now if you further see, what will be the case? In which case it is correct. So if you see here, along with this, we are getting another peak here, that near about it is 1600, and due to C double bond C. Okay, it is due to C double, and C double bond C is present in both. Okay, now the inferences are near about same. C double bond C is at 600. It is present in both the cases. Okay, C double bond is also present at their own position, and it is also true. So what is the answer? Exactly B or C, and why? So if you see the B case of the B, okay, case of the B. So there is one phenomena is occurring here. I will just write that phenomena. I will just draw, and you will be getting very quickly what is that phenomena. So what is this phenomena? That is possible in B, and this is not possible in C. What is this phenomena? It is, just quickly write. Very correct. It is resonance. So what is happening? This structure, it is not all the time. This C double bond C is not all the time double bond, or not C double bond O. Not all the time it is a double bond. Okay. Somewhere the another resonance hybrid of this structure will be like this. Okay. So what is happening? If you are considering it is an answer, so this value should be shifted to slightly to the left hand side, because the value is decreasing. It is not 100% on the double bond character, and also this value should be shifted to slightly to the you can say the left hand side. Okay, but if you consider here, there is not the resonance possible. This is all the time in the its double bond state. Strong peak is there, and this is a separate entity as a C double bond O, so it is its own position is there. If these two peaks are might have appeared the original position is 1600. If it might have appeared at 1550, and this might have appeared at instead of 1700 1600 and something 80 or 1690, due to this resonance the value will be decreasing. Okay, but it is not the case. Okay, so we also ruling out this. So our exact answer is this one. So in this way, this aromatic compounds, I told you the specific cases we can see here. Let us see one example here from the drug molecules. So here we are having a molecular formula, that is C4H9NO. C4H9NO. And say, for example, this is the spectra is given to you. Okay. So what may be the, you can see the answer. What may be the answer? Okay, no problem. We will see. So here, if you just calculate the HID of this compound by using this formula, 2C, or you can say 2C minus H plus hydrogen plus oxygen plus 2 divided by 2. So you just calculate it, you will be getting it near about, it is 1. So what does indicate? That there are 4 carbons we are having in this molecular formula, only 4 carbons. So it cannot form a aromatic ring. Okay, so this compound is not aromatic. Another say the structure is also saying that there is no overtone combination overtone bands, small bands, which is observed in the aromatic. So it is not the aromatic one. So it is an aliphatic compound. Okay, it is an aliphatic compound. So it is containing nitrogen and oxygen also. It is containing nitrogen and oxygen also. So if you see carefully here, I told you very strong band is appearing here. Near about you can say 1600, 16, 20, 40. This is 1700. So very strong band is appearing near about 1680 something. Okay. So what does it indicate? It indicates that oxygen is there, and this bond is very strong bond is there. So we can consider it is a C double bond O. Definitely it is there in this molecule. Okay. Now we have to minus this from this molecular formula, C double bond O. So what is remaining? C3 H9 and N, because C double bond O we have removed. Okay. Now another thing, we can see here very specific pattern. Just last time I told you the peak is splitting into two. If this peak is like this, like a tongue, so we might have told closing our eyes that it is OH, but it is not the case. If it is a single sharp line, then we have told it is NH, but it is not the case. It is the splitted into two. Okay, so you can remind what is that. I told you it is NH2 now, because of the symmetrical asymmetrical stretching, because of this region. Okay, so we got the another fragment NH2 of this molecule, NH2. Okay, another thing, that this C double bond O is appearing at 1680. Just go back and tell me here amide, very less lowest of all C double bond O, amide. So that C double bond O and NH2 we can combine. We can combine. So we are getting this fragment. So amide is functionality there. So we can minus this NH2 from this formula. So we are getting C3 H7 remaining, and that C3H7 is not nothing but our aliphatic groups. So we will be coming to know that our expected compound is this one, because we are getting here CH3 is 3, very sharp peak at 2900. So it is due to this CH3. Okay. So here, this is the you can say it is given in you can say the book that is William Kemp, and also the Silverstein. Here all the peaks are combined in one graphs, one image. You can refer these values. This is the website. You can note down here a spectral database for the organic compounds. So how it is useful? Some of you might be knowing it. I'm going to website and I'll find you what is the how it is related to our today's presentation. Okay, so it is a DSBS. Sorry, it is SDBS. As in Google, you type SDBS, a spectral database for organic compounds. SDBS. So here, uh, you have to first click on agree to the terms and condition of the SDBS. How useful for the your spectral data analysis this website. So if you want to find out the reported IR spectra of say paracetamol, so type here name of the compound paracetamol, spelling correctly, and type here search button. So you will be finding this ESR, Raman, IR, HNMR, CNMR, mass of paracetamol. I'm just clicking here. 4 hydroxyacetanilide is the IUPAC name. So this is my structure of paracetamol, and here I will be getting the mass, CNMR, by clicking on the IR. So we'll get the IR of the paracetamol. Okay, now just whatever you have learned till now, we'll be comparing. We'll be just checking our knowledge here. So first of all, we'll draw a line here. Sorry. We'll draw a line at 3000. So here you will be getting a sharp peak in this region. Can you see this very shoulder peaks at 2900? This shoulder peaks. If you you can say zoom it, you will be able to see it properly. So this shoulder peak is due to this CS3, sp3, ch. Okay, and you will be finding here uh, the peak. The two peaks are merged in this region. The two peaks are merged. One peak is you can say, if you remove this sharp peak, the peak will be like a tongue. Okay, like a tongue of that we saw. I told you the OH. But as you can say, the NH is also present and OH is also, two groups are present in the same region. So that sharp, you can, the broader peak of the OH is distributed into the two. One is due to the OH and another, this sharp, you can find it is due to the NH. And this NH is secondary. It is not divided into two because it is a secondary. So this peak is due to this NH, and this broader peak is due to this OH. Okay, can you see something here? Can you see something here? What I told, this is the characteristic for, is the characteristic for aromatic ring, aromatic compound. Okay, I will tell the website to you. Don't worry. A very useful website is there. I will give the website to you. So this is for the aromatic compound. So you can say the aromatic ring is also confirmed. You can see the,
No screen.
yeah.
Screen is not there.
Oh, wait. I think screen sharing.
Yeah.
Okay, can you see the screen now?
Yeah. Yes.
Okay. Okay, can you see the desktop? All of you, can you see the, yeah.
Yes.
Okay. Okay. Now, what is appearing on the screen?
Google.
Okay. All the delegates, you can see Google is there. Na? So you type there SDBS, spectral database for the organic compounds. Okay. Can you see? So I'm opening this SDBS. Okay. So if you open this SDBS, it will ask for the to agree the terms and condition. You click here, and can you see this name of the compound here? So you have to type the spelling properly. I'm typing here paracetamol. Spelling should be proper, and you click on this search button. So what is available for the paracetamol? ESR is not Raman, IR, HNMR, CNMR, and MS. So just click on this compound number of paracetamol 3290, and the structure is in front of you. You will get the 4 hydroxyacetanilide, its IPC name. And if you click here on the IR taken in KBR, so you will find the spectra. Can you see the spectra of the paracetamol here, all of you?
Yes.
Okay. So and I will repeat it. So in this spectra, if you draw a line from 3000, a line from the 3000, so you will be getting here very small shoulder peak. This peak. Can you see this peak? Very small and shoulder peak. Okay. It is 2900 peak due to this sp3ch. Okay, as I told you, sp3ch. Now you will be observing here a broader peak. The actually this peak is like a tongue, broader peak, but it is divided into a sharp peak also. So why it is so? If you see the structure properly, here is the OH and NH, and both are coming in the same region. If you remember, the The OH is a broader peak, like you remove your tongue outside the mouth, so it is OH. And NH is also in the same region, but it is a sharp peak. So both are combined here. Okay, so these two peaks are there. The one was actually broader but become little bit sharper due to the NH, due to this OH group, and the another sharp peak due to this NH. And this NH is not bifurcated into two. Okay, it is not bifurcated into two because it is a secondary amine. It is not the primary amine. So because it is secondary amine. Okay, if it had been a secondary amine, so definitely we would have got it a two peaks. So it is clear this part, OH and NH, and this CS3 small peak. Okay, if you see a sharp peak here, sharp peak. Okay, uh, maybe it is around it is 1600, 1700, 1715 something, 1715 or 20. This very sharp peak. So I told you one thing, sharp peak in this region may be due to C double bond O. Okay, so it is a C double bond O due to this ketone, as you told you in the spectra in ketone. So, and you can see this one. This is a very characteristic pattern. This one, what is for this? Where the mouse is there? I told you, whenever such type of the structure is appearing in your IR, close your eyes and tell that aromatic ring is present in my structure. It is very specific for the. It is a combination of the orton for the aromatic compounds. Close your eyes and tell that aromatic ring is there in my structure. So it is indicating of this. You can see this peak. This is C double bond C of the aromatic ring. So how many peak we are solved? We solved this OH. We solved this NH. We solved this CH3. We solved this C double bond O. We solved this aromatic C double bond C, and we solved this or combination of ortons of aromatic. So our structure is proved. Similarly, if you want to search another spectra, you can see here so many things about your mass spectra of your paracetamol. You can get this is the mass of the paracetamol. You can take the H1 NMR of the paracetamol. You can take the CNMR of the paracetamol. Okay, so it is a very useful site. I will go back and I will now search ibuprofen. So it is a, just in Google you type SDBS. Okay, S for structure, D for data, B for base, again S for structure. And I typing here another compound name, that is ibuprofen. Click on this search button. So here your ibuprofen is here. Your ibuprofen structure is there. You can find the mass of the ibuprofen. You can find the C13 of the ibuprofen along with the values. You can find out the IR of the ibuprofen in KBR in the usual mole, both techniques. So this website, n number of the molecules are available. You can say heterocycle, you can say substituted heterocycles, you can say large number of the drug molecule available on this website, and their database is available. But here if you open this database, the first time it is asking that yeah, I'll show you. I agree the disclaimer of the SDBS. So what does indicate that you will not use this database for your thesis purpose. Okay, sometimes the structure, say for example 2-methyl pyrrole, 6-amino pyrrole, as a intermediate you are preparing in the lab, and that molecules actual spectra is also available here. So you may be copy pasting the spectra instead of actual going through the spectral analysis. That's why the site is saying that you should not use the data. You, as a reference only, you have to use this data, not for copy pasting and using for your research purpose. So you can find your compound with the help of molecular formula, with the help of name, with the help of molecular weight, or if you are having the chemical registry number, or if you are having the SDBS number, you can find out so many things from this website. So you can use this website and you can practice more molecules of the IR study. So here with this I used these books, William Kame, I used the Silverstein and I used the Skoog. These are the very nice books. We should refer these books. Make a habit of reading these books because the books will give you a lot of that knowledge which you will not get from the online materials, ready-made video lectures. So simultaneously, you have to read the books. So I collected all the information from these books.